Now question number 6 says, an ideal gas enclosed in a vertical cylindrical container supports a freely moving piston of mass m. The piston and cylinder have equal cross-section area A. When the piston is in equilibrium, the volume of gas is V0 and the pressure P0. The piston is slightly displaced from equilibrium position and released. Assuming that the system is completely isolated from its surrounding, the piston executes simple harmonic motion. You have to find the frequency of that simple harmonic motion, and Prasoon will explain us how.
Okay, so this question involves concepts from mechanics also. So let's get a rough idea. Let's just understand why SHM will be there in the first place.
Exactly.
So this is our cylinder, and suppose this is some piston, and it is kept here isolated from the surrounding. That part is very important. Now there would be some, this would be having some mass mg acting downward, and here would be some pressure.
Correct.
So in the equilibrium condition we have mg equal to pa,
right,
which is basically p naught a as it is given in the question.
Right.
And this would be like stable. Now if we just push it downwards, push it a little bit downwards, then some process would happen, some thermodynamic process would happen, because of which, see, like this was y, this is y minus dy.
Right.
So some pressure change would happen, because of it, it would try to go back into equilibrium, because pressure was the only one which was responsible for basically holding this up, opposite to mg. So this pressure changes little bit, because of which a resultant force would be there. A resultant force and resultant acceleration would be there, and we have to measure that resulting force or resulting acceleration, and using that we are gonna find that it would be an SHM, and then we can find the frequency.
Correct.
So one very important thing is here, that what type of thermodynamic process might be going on, because see, we have the volume, we have P, and we have to find some relation between them so that we can go on with the question.
Right.
So what we are given here is that the system is completely isolated from its surrounding, which means that there is no heat exchange or there is no interaction from the system and surrounding.
Right.
So the process which it will undergo would be an adiabatic one.
Correct.
Adiabatic process. So now let's start or see the maths how it is done. So for an adiabatic process we have PV to the power gamma is constant, some constant C.
Right.
Now we start differentiating it with respect to P, say. So dP, we do this differentiation basically to know the relation, the differential relation between V and P.
Right.
Because the change you see is very small, so we'll need differentials here to solve the question.
Right.
So dP V to the power gamma plus gamma P V to the power gamma minus 1.
Right.
dV would be equal to 0.
Correct.
We have dP by dV, which will come out to be minus gamma P by V. Now see, here we get another variable. We know that this will be valid throughout, but what would happen, because we cannot know every P and V.
Right.
That was the main problem in the first place. So we note that this dy, this change which we have made, is very small when slightly displaced. That is the word that has been used in the question.
Right.
So slightly means there would be no appreciable change in the value of P and V from the initial one. So this we can substitute as by P0 and V0, which were the initial values.
Right.
Okay, so we get dP as basically the change in pressure of the inside as minus gamma P0 by V0 into dV.
Correct.
Okay, so now what is dP? dP, now we get some idea that yes, the pressure is changing, so some force might be acting on it.
True.
Now we just try to relate that force to the pressure. So let's go on. dP is actually the force that would be, we know pressure equals force upon area
Right.
The area is constant in our case. So since the dP changes there, it would result in a dF force divided by area.
Right.
And dF would be equals to dP into area.
Right.
So basically the force we have is dP into area. dP will be equal to dF. dF will be dP into area. Okay, let's just substitute it for dP here. So we get dF by area would be equal to minus gamma P naught by V naught. Now what would be dV? Let's see, we moved it down by dy.
Yeah.
The area of the piston was the same as the cross section, so area was A, and let's say this, and we move it by dy. So the corresponding change in volume that occurs is A dy.
Correct.
We write that down here, dV as A whole into dy. Now we write down the formula for dF equals minus gamma P naught by V naught A square
Yeah.
dy.
Okay.
So we get this formula for dF. Now since we were talking about the acceleration of our piston, the piston execute SHM, the mass of the piston is m, so we can denote it by m into the resulting acceleration that occurs on it, which tries to bring it back, equal to minus gamma P naught by V naught A square dy. And since it undergoes in SHM, so for SHM, m into A is equal to minus omega square into the displacement, which is equal to dy here.
Right.
So we cancel these out. We get omega. See this. This is actually mass into acceleration. So this is the whole force.
Right.
And this would be minus m omega square dy, because acceleration alone is equal to omega square dy, and we have to multiply it by m. So finally we get omega as gamma P naught A square by V naught whole into m. So
and the root of that,
this is equal to like omega square, so yeah, omega, this would be the root of that. This is equal to 2 pi f. We were asked the frequency,
right?
So frequency would be 1 by 2 pi gamma P naught A square V naught m.
Right. So guys, we found the frequency of the simple harmonic motion as asked in the question, and we saw an important formula here. For the simple harmonic motion, the force equals minus omega square dy, which helped us get to our solution. We'll see what happens in the next question now. Now in the seventh question, you've got a fixed thermally conducting cylinder that has a radius r and height L0. The cylinder is open at its bottom and has a small hole at its top. A piston of mass m is held at a distance L from top surface, and P atmospheric is P naught. Now there are three parts of this question. The first part is that the piston shown in the figure is pulled out slowly and held at a distance of 2L from top. The pressure in the cylinder between its top and piston would be what?
So basically we know that there is a hole in the cylinder.
Right.
So because of that, you see the pressure in the outside is P naught, and so the inside also it would be P naught, because if it is not there, then there wouldn't be equilibrium, and to maintain that equilibrium the pressure would flow in.
Right.
Like the air would flow in, and so the pressure, if the hole is not sealed and if the hole is continuously there, so even if it is brought to some distance, say L or 2L, initially the pressure might be less because the volume is increasing. Then because the hole is allowed to be there, the pressure will equalize. So the final pressure which will come out on the interior would be P naught.
Correct.
So this is a very easy question, just because it requires the basics.
Mm-hmm.
So the pressure would be P naught.
Okay, we'll move on to the second part now. The second question says, that while piston is at 2L from top, the hole at the top is sealed. The piston is then released to a position where it can stay in equilibrium. In this condition, what is the distance of piston from the top?
So let's analyze this question. Now it is sealed. So because of that, we have, say, this is a cylinder. It was like this, and here we have it compact.
Right.
So initial was P naught pressure, and here also it was P naught and mg. The mass is acting. Okay, so it is like this. Now, since it is released, we say that it goes. It will go downwards because this mg is acting downwards. So it will go down and stop some distance. Say this is the piston in the final position. This is 2L plus X. This initially was 2L. This is 2L plus X when it goes down. Pressure here finally is P. Pressure outside is as usual like P naught, just like before. And again it has mass acting mg, but in this time it is in equilibrium. Therefore the area, this area of the piston into pressure plus mg would be equal to the outside pressure into the area. So the pressure would come out to be P naught minus mg by A, where A is the radius, is the area of the piston.
Correct.
Now because the temperature remains constant, because of that we have P initial whole into V initial would be equal to the final pressure whole into V final.
Right.
Now this is so because the pressure would be the same as the outside, the temperature would be the same at the outside temperature, because it is given that the temperature can maintain itself, hence the temperature would be constant. And we can apply Pi Vi equals P final V final. So let's do that. The initial was P naught and the volume was 2L into the area, which is pi r square, equal to the final pressure P naught minus mg divided by pi r square, whole into the final volume 2L plus x into pi r square. So on solving this, we get 2L plus x equal to P naught into 2L into pi r square by P naught pi r square minus mg. Send 2L there and we've got our x.
Right. So we'll move on to the third part of the question now. Now the last part of the question is that the piston is taken completely out of the cylinder now. The hole at the top is sealed. A water tank is brought below the cylinder and put in a position so that the water surface in tank is at the same level as the top of the cylinder. Density of water is D. In equilibrium, height h of water column satisfies which of the following conditions? Proceed.
So we start by drawing the diagram. We have this water container. In this we've kept the cylinder.
Right.
And this is the air which gets filled. So this is the height h. And this was hole L naught.
Right.
So basically to find the solution, we look at this particular depth. And at this particular depth, the pressure should be the same for water here and water here.
Right.
So we find the pressure at depth. First we find the pressure at depth L naught minus h. So the pressure at L naught minus h would be rho rho, that is our D density,
Right.
into L naught minus H into G plus P naught.
Correct.
Now the pressure of air in the cylinder, what is that? So the pressure of air in the cylinder, this we have to find. So basically we are finding that at this particular point, the pressure due to the air and the pressure at this should be the same.
Right.
Because they are at the same height below
Correct.
the water level. So for that we have P naught, basically P1 V1 equals P2 V2. We separate this equation. This was the pressure at depth L naught minus H. So now we come back, P1 V1 equal to P2 V2. So we have here this point P2.
Right.
So P naught whole into L naught into pi r square would be equal to P2 L naught minus H whole into pi r square.
Right.
So P2 comes out to be P naught L naught divided by L naught minus H. Now since they are at the same depth below the water surface, the pressure would be the same.
Right.
So we equate those two pressures. So P naught L naught divided by L naught minus H would be equal to D, which is the density,
Right.
L naught minus H into G plus P naught. Now we cross multiply, we get P naught L naught equal to dg L naught minus H whole square plus P naught L naught minus H.
Right.
Now we send it that side, dg L naught minus H whole square plus P naught L naught minus H minus P naught L naught. Go back to the options, so it coincides with the third option, hence the third one is the relation.
Right.